Shall we? Let's do it. So what did we talk about last time? We kind of did the little control history thing. Oh no, sorry. Yeah, history. I'm not messing this up. What else? We did like this deterministic optimal control stuff. Talked about the problem setup. And we're going to spend most of our time on that deterministic optimal control thing. Later in the course, we'll do a little bit of, the stochastic stuff, some other sort of tweaks to the setup. But we're going to spend a lot of time on this problem because it's like probably the most useful. And last time we derived Pontryagin's, I'll just call it Pontryagin's principle. The min or max is a matter of taste, let's say, depending on if you're like a more controls or learning person, or if you like mins or maxes better. And so we talked about that. That's basically KKT conditions for an optimal control problem, right? And we derived it in discrete time, literally just from writing out the KKT conditions, right? And coming up, defining this Hamiltonian thing and setting gradients equal to 0. And then I just kind of teased at the end, I just wrote down the continuous time version as well as ODEs. And it looks exactly the same. It's no big deal. You can derive it in continuous time via calculus of variations, or you can just take a limit of the discrete version, and it's very straightforward. But I hope you trust me that it's like, they look the same. It's pretty obvious how to do that. And you'll see the old school classical literature on optimal control has a lot of stuff from that Pontryagin principle kind of viewpoint. And there's a lot of like cases where you can try to find, closed form solutions for the optimal things in various ways. But I would say, generally speaking, it's like not that useful, or say numerically, there are better things to do. And that stuff sort of fell out of fashion maybe in the 80s as computers got better and stuff. Okay, so today we're going to do, we are going to do LQR 3 different ways, because LQR is super important. So I'm going to tell you what that is first, and then we're going to do LQR via Pontryagin with a shooting method, which we kind of talked about last time, and show you how that looks. And basically, it's how to do gradient descent for an optimal control problem while you exploit that, like, Pontryagin structure. It literally looks like backprop from deep learning. So if you've seen that before, it's that where you replace like your activation functions with your dynamics, basically, right? It's forward rollout through the dynamics, backprop gradients through the dynamics Jacobians, that kind of thing. So we're going to do that, and then you'll see. I will show you that is not a great algorithm in general, and so we'll then look at it a couple other ways. We'll see it as a QP, a quadratic program. I'll show you exactly what that means and what that looks like. And then finally, we're going to derive the Riccati recursion, which will lead us into some other topics, namely dynamic programming next time and stuff like that. And there's some fun connections there too. Okay, any questions about any of that? That's what we're going to do today. All right, let's do it. So the first thing to talk about is this LQR problem, which is a big deal in control theory. This is like, it is the optimal control problem that we can solve in closed form. So therefore, we like to, this is sort of the playground of control theorists. It's the stuff where you can actually like prove things and like get nice closed form results. So it's very big as a theoretical construction. And also it's super, super practically useful as well, because you can basically approximate any nonlinear control problem locally as an LQR problem. So it shows up all over the place whenever you linearize, right? Approximate anything locally. Like the linear approximation of every control problem is an LQR problem, basically. So it's this like sort of super, super useful thing all the time. So you'll see this everywhere. And in general, if you have a nonlinear problem, if you can approximate it as an LQR problem, you should. Like, it's the thing to do if it works. It's like basically always the first thing to try. Okay, so what does this thing look like? So going back to like, we defined, the general problem last time. It's a special case. So we've got, our control and state trajectories that we're optimizing with respect to. And we have a cost function that in the LQR setting is a quadratic cost. That's the Q. So let's write that down. So here's like kind of a, not the most general quadratic cost. So we'll tweak this later, but this is kind of a good place to start. So that's our state cost. And we have a control cost. And then we have a terminal cost. So the sum goes, k equals 1 to n minus 1. And then we have a terminal cost that's just on the last state, xn. So the idea, right, is if I start at k equals 1 and make control moves, like at k equals 1, u1 gets me to k equals 2, right? So I end up basically having, like, in discrete time, if I stop at time n, I have a control input at time n minus 1 that maps me into xn, and then I'm out of control moves, right? So there's like one fewer control than state. Is that clear to everybody? So at time n, you don't have any more control moves. You just have a final state. So that's why there's this terminal cost that's a little different. It's because there's no control at the last time step. There's just a state that's the last one you end up in, right? And then you can't do anything else. So that's why it looks like that, right? Okay, so that's the cost function, quadratic cost. And then we have linear dynamics. So this looks like xk plus 1 equals ax plus bu. So A and B, right, matrices. So this is just a slight specialization of the general nonlinear problem we saw last time, where you have quadratic cost function and linear dynamics. So that's the linear quadratic regulator. That's what the LQR stands for. Regulator is just like an old name for controller, right? So that's what it means. And there's a couple of requirements on the setup that, like, it'll become a little bit clearer why. So there's some requirements on specifically on those Q and R matrices in the cost function. They have to be, so like normally for a QP, we want things to be like positive definite or positive semi-definite. It turns out in this case, for reasons that will become a little bit clearer later, you need Q to be positive semi-definite, and you need R to be strictly positive definite. And this will become clear in a little bit when we get into the math. Basically, turns out that you have to invert R inside, like, when you solve this thing, and so R has to be strictly positive definite to get unique solutions. Q, you don't have to directly invert, and so it's okay for it to have some zero eigenvalues and stuff. And you can think about trivially, if Q were just zeros, it means I don't care about my state at all. So if Q's all zeros, then basically the optimal controls are zeros also, like trivially, right? So that's legal, and you still get a decent solution. Whereas if R's got zeros, it means there's no cost on arbitrary controls. So what that does then is, if I have any state cost and there's zeros in R, the optimal thing to do is to like have infinite controls that get me to the goal like instantly, right? So that's why R has to be strictly positive definite. If it's not, if there's any zero eigenvalues in there, it lets you have infinite controls. So to have bounded control solutions, I need R to be strictly positive definite. Does that make sense to everybody intuitively? That's why those things are the way they are. Okay, cool. So some notes on this. That's the problem. Cool. That's it. No other constraints, by the way. Just that. No extra state or control constraints in the sort of vanilla setup. And then some notes. This can locally approximate like many nonlinear control problems. And if you think about it, if I do Newton's method on a nonlinear optimal control problem, where I take, second order Taylor expansion, blah, 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 the Newton step that I solve on a nonlinear program is an LQR problem, basically. Does that make sense? So this is why this shows up everywhere. Like, it's the local approximation. So anytime I take a Taylor expansion of a nonlinear problem, this is like the first or second order Taylor expansion of arbitrary nonlinear problem. So it's the thing that shows up in the inner loop a lot of times when you're doing nonlinear stuff anyway. The other thing is, this thing is basically, we know everything about this. We know how to solve this. There's like, you can solve it really efficiently and fast. So there's like, it's very computationally nice. And then the final note is that, like, this is kind of the one we're going to look at today. but there are many, many generalizations and tweaks to that set. I was always saying this is sort of like the playground of control theorists. And there's a like kind of an old saying. I don't know who said this. I want to say it's probably Art Bryson of Bryson's rule. That this has been called the crown jewel of control theory. It's like basically super useful. We know all the answers, right? It's got analytic solutions, like all this kind of good stuff. And so there's lots and lots of things you can do on top of the basic setup. So there's many like variations on this theme. So for example, this is called the finite horizon problem. You can also have the infinite horizon problem where you take n to infinity, and like there's a limiting solution to this in a lot of cases, which we'll take a look at later. There's also a nice stochastic generalization of this that we'll talk about later in the course. There's lots and lots of other tweaks to this setup that still give you like, yeah, interesting things.
When you say locally approximate, you mean linearized?
Yeah, I mean, basically, if I were to take, like a first, second order Taylor expansion of a nonlinear problem, this is what it looks like, right?
But that we anyway do, right? DFDX, that A equal to DFDX.
Yeah. So
that related.
That's it, right? If I linearize my dynamics and take a second order Taylor expansion of my cost, that's what I get. So literally, this is a Gauss-Newton approximation of any nonlinear control problem.
I mean, yeah. I mean, once we have a nonlinear system generated, then we can write it.
That's right. Yeah. So my point is, yeah, if I were to do Gauss-Newton on any nonlinear problem, this would be the Gauss-Newton step, right? This is like what I would get if I linearize the dynamics constraints and take a second order like quadratic expansion of the cost function. I get an LQR problem. So we're like, when you go to numerically solve like a nonlinear problem, you're basically your inner loop is an LQR problem. So it shows up all over the place. Does that make sense? Cool. With like, minor variations depending on the details, right? Newton versus Gauss-Newton, blah, blah, blah. There's some subtle variations, but like you end up solving basically LQR problems all the time, even when you're doing nonlinear stuff. Okay, cool. So the first thing we're going to do is, now that you know what this is, we're going to spend a lot of time on it. The first thing, though, is to go back to what we did last time and write down the like indirect shooting thing and just do it on this problem. So I'm going to just write that out real quick. And I'm going to write it quickly in the interest of time, since we talked about it last time, but you are encouraged to go back and like derive this yourself. It's super easy. I'm just going to plug in this cost and dynamics into the Hamiltonian, Pontryagin stuff from last time, and like just write that out real quick, and then I'll show you the code. So it looks like this, right? This is lambda of the Hamiltonian, and this is just the dynamics. So that's and also here I'm going to do the time invariant version, so that A's are all the same for all K. And okay, we should write this out. Time invariant if AK equals A, BK equals B, QK equals Q, RK equals R for all time varying otherwise. So if the matrices are the same for every time step, time invariant, but in general, they can be different at each time step. And so right now, I'm just going to write it out for the time invariant case, just because it's easier and like less bookkeeping, but you can have subscripts on all of the matrices as well, right? Okay, cool. So here's the lambda stuff. So this looks like the following thing. Again, this is just plugging into the stuff from last week. And then we get lambda n, this like terminal boundary condition thing. It's Qn xn. And then we get u equals argmin u tilde of h And it turns out here, so remember last time we said we wrote it down like this with the argmin so that we could handle torque limits on U. Here, though, we don't have any. So you can do that in closed form. You can just, the argmin, you can just take the gradient of the H with respect to U and set it equal to 0. And so if you do it, you get the following thing. Okay, so yeah, I'm just going to write it down. You can plug and chug and try this yourself. Okay, and so that's the math, and then the procedure for doing this kind of thing is you start with an initial guess. Then you simulate forward or roll out. To get your X trajectory. I should write here, you need a guess on the U's. Then you simulate everything with those U's. Then you do a backward pass using the lambda equation right there. So that will give you the lambdas and the U's, like new U's, right? And then you roll out with a line search. On the U update. I should write like delta U here maybe. And then basically just repeat this. Until convergence, right? So if you kind of look at this and think about it for a minute, like this is literally just doing gradient descent on the U's. And this is just a recipe for computing the gradients efficiently by like backpropping through the dynamics. So it's literally like just like backpropping a neural network, but it's through time, like through the dynamics instead of your layers in your neural net or whatever. Okay, cool. So okay, that's what we're gonna do. And before we do it, I'm gonna just make sure. So this is the dynamics we're gonna do it on. We're gonna do it on a so-called double integrator. Who knows what I mean by that? Hands? Not too many. Okay, good. Then I should tell you about it. So this is like kind of the simplest dynamics function you can imagine. It's I'll write it down. It's F equals ma for like a unit mass, particle. So there's our state derivative, and the dynamics look like this. So that's saying, Q dot equals Q dot, and then we get a control input on Q double dot. So it's like having a particle in 1D with F equals ma, where F is your control input and M is 1, right? That's what that is. So maybe write some of that down. So this is, acceleration. This is velocity. This is your force. This is your position. And like you can think about this as like kind of the intuitive thing to think about here maybe is as like a sliding brick on ice, like a frictionless, and you get to, push on it, and it's in 1D. It's like sliding on the line or something. Everybody cool with this? Just writing up, yeah.
From continuous system to discrete system, the H is different, right?
We're gonna do it right now. Yeah, so okay, that's continuous time. It's literally just F equals ma for unit mass and U equals F. And I just wrote it like a 2D state space system. Now we're gonna discretize it. And so here, like I can do this one in closed form. I don't need to use like a Runga cutter or anything because it's like we know what the solution to this is, right? So here's that. Xk plus 1 equals. So if I have some time step h, it looks like this. So this is qk, q dot k. Is everyone cool with that, right? So I just like, you know, it's qk plus a, you know, little time steps times q dot times velocity. And then the acceleration term, the B matrix looks like this. So it's obviously, you know, I get an h times the acceleration, and then I get a 1/2 at squared kind of thing on the position. So that's your UK. And so this is your A. So someone, yeah, what's up? Those are H's. Yes. They're the time steps. Oh, QKs, yeah. Those are Ks. These are Ks. The little subscripts are Ks. And the H's, the bigger things are H's, which are the time steps. The subscripts on the Q's are Ks. I realize my handwriting is not awesome. I apologize. If you have any confusions, let me know for sure. Okay, we cool? Yeah, N's are like, I'm always going to use K's for like time index subscripts. N's always the last time step. Big N is always the last time step. H is always the time step, you know, duration, the delta T. I'm pretty consistent with that. So hopefully the context and the consistency help with the interpretation of the terrible squiggles. Okay, that said, yeah, if anyone wants to LaTeX these and help with like that effort, we actually have someone who took it last year, like actually did a bunch of LaTeXing of notes, and I have those. And like, I would be super psyched if we could like have a rotating sort of like scribe LaTeX situation. If anyone wants to like do that, I think it'd be awesome. We can talk about this. I think LaTeXing these notes would be great. I'm in favor of this. So yeah, in the meantime, bear with me. Okay, let's see. Oh yeah, this is, let me just write, like this guy is the B, right? The discrete time B. And then yeah, like the H here. That's it. Cool. Everyone cool with that? See how I did that? Cool. All right. So that's that. Let's go do it. Hopefully we're all cool with here's some code. So here's the shooting thing. Let's fire this guy up. Oh yeah, you guys want me to zoom in, right? Let's try. Is that okay? You see that? Okay, cool. Okay, so this is here's the dynamics I just wrote down with like h equals 0.1 second, so like 10 hertz. It's literally, you know, the matrices we just wrote down in the notes. Here's just some setup stuff. So I'm going to make the you know, trajectory 5 seconds long, and number of time steps, whatever, for 5 seconds. You know, initial conditions. I'm going to start it at like x equals 1. Like so q equals 1 and like 0 velocity. So I'm like a meter off from the origin, stationary, and the goal is to push me to the origin, right? That's what the cost function says. So if that wasn't super clear, it's a quadratic cost function that's penalizing x, right? So that's minimized when x equals 0. So the whole LQR thing, the goal is to drive you from whatever initial conditions, x naught, to the origin, to like x equals 0. That's always kind of what this thing is trying to do. Okay, so that's initial conditions. Cost is super dumb. I'm going to make it, you know, identity on the Q. So identity, you know, so the state cost is just, you know, x transpose x, and then 0.1 on the controls. And we can play around with this in a sec, and I'll show you what happens for like different values. So this is the cost function. It's just adding that up. It's exactly what I wrote down, right? So if I have a sum over k, and like, you know, that's what it is, right? No surprises. And then this is like the terminal cost kind of separated out, right? Cool. Here's a dynamics rollout. So it's just like straight up going AX plus BU, you know, in a for loop. along the trajectory. Here, I'm going to make an initial guess for like X and U. What did I do? Did I make this ones or something? Oh, I think I just made, I just made the controls all zeros. That's cool. So we're going to roll it out with all zeros. That's my cost if I just sit there and do nothing. Just adding up the cost function over time. So it's like 25.5. Cool. Here's the meat of the algorithm. So I'm going to put a pretty coarse tolerance on like my line search convergence stuff. This is like my backtracking stuff. Oh yeah, this is my termination condition is like, again, pretty coarse, like only a couple significant digits because it's going to take a really long time to converge. And then here's this. So I do the rollout, and then this is the backward pass. So I start at the end with my terminal condition on lambda, right, which is qn xn. And then I just go backwards doing the u stuff and the lambda stuff from what we wrote down till I get to the first state. There's one subtle thing here, which is in the notes, I wrote it down as u equals, this guy. And because I'm doing the line search and I actually want delta u in order to backtrack on delta u in the line search, I want delta u and not u. So in the notes, I did it for u. Here, I'm taking, I'm computing delta u by taking like basically u minus the u naught. Everyone cool with that? That's like y. So I can do a line search on delta u. And then the lambda stuff is stock, exactly what we saw. This is just Armijo. And there's nothing in there. We already saw that. Nothing super interesting. So yeah, we're going to run it and look at what happens. So like 600 and change iterations. What's the cost now? 6.5. So that's a lot better, obviously. And let's like look at the solution and see what it looks like. So that's seems reasonable. I start at like, x equals 1, 0 velocity. And I like, pushes me towards the origin. That seems cool. What do the controls look like? They're sort of big. And then like, so I actually do like, hit the gas pretty hard. And then I'm actually hitting the brakes to like slide in, at 0 velocity. That kind of all makes sense, like not super surprising. Let's do a couple things. So this was a 5-second horizon. I wanted to show you something real quick. Let's set this to 10 seconds instead and see what happens. So we'll run the exact same code. The point I want to make is actually this is going to take a lot longer. It takes a lot more than twice as long is kind of the message. In particular, you'll see, so it's still sitting here. And let's look at the iteration count now. It's like a lot more iterations. Does anyone have any thoughts on like why is that so much worse? And we can look at the solution too. Let's do that. So, pretty similar, whatever. This looks pretty similar. It just sort of like, gets to 0 and then sits there, which is kind of what you expect. So all these, there's no like surprises in here. It looks basically the same. Does anyone have any guess at why it like took so much longer and seems to have been a lot crappier with like twice the horizon length? Anybody? Okay, so this is like the controls version of the like vanishing and exploding gradients phenomena from deep learning. Like basically you're backpropping through these time steps. So the more of them you have, the like more you backprop, the kind of the worse your conditioning gets. Actually, that like vanishing exploding gradients thing, the control lingo term for this is the tail wagging the dog problem. Is what it's called historically in control. Basically, if you have really long horizon on your trajectory and you're doing this backward recursion, you get like, error compounding and like gradients get nasty the longer you do this. And so this is, and I should also mention, this is a linear problem, right? This is actually as easy as it gets, and it still kind of sucks here. So if you try this on a nonlinear problem, these methods get like really nasty and don't work well. Okay, that's, I don't know, lesson of the day for that. Anyone have any like, I don't know, questions on this or want to try anything weird? What should happen if I make R, what should happen if I make R bigger? If I make R1 instead of 0.1, what will happen? Yeah, because I'm making the controls more expensive, so it'll use less control. So it'll like take longer to get there, right? Okay, cool. Yeah, we won't mess with this now. We'll do it. Okay, I'll do this. Like we're gonna do more of this, so we'll see that in a sec. Everyone cool with this? Yeah.
Is it is the cost approximately quadratic in the time? I mean, I don't know if it's just a coincidence.
The algorithm cost in the time horizon?
Yeah.
Yeah, we'll see this in a sec. We're gonna show. We'll derive the complexity of this. Turns out it's linear in time, which is not obvious yet, but it'll become more obvious.
Yeah, we doubled the time horizon.
And it got a lot more expensive. Yeah. So it's not, yeah, it's not. It should be linear. So the cost of computing the gradient is linear in the number of time steps, right? That's kind of obvious. I just chain more of those steps together. And if you do this right, it should be linear in the time horizon in terms of like overall complexity. This is coming from something else. It's coming from this like sort of tail wagging the dog, ill conditioning issue when you have longer horizon. Yeah.
So when you're saying like issue with gradient, like when you're propagating back and forth, are you referring to kind of like a accumulated error?
Yeah, it's accumulated error kind of thing. I mean, you do definitely run into like floating point round off kind of stuff, but there's this bigger issue of like, so one way to think about it is I have that A matrix, right? And when I backprop everything, I'm backpropping through the A matrix. So like that thing is effectively getting like raised to the nth power. And so if A, whatever the condition number of A is, so if like A has big spread in the eigenvalues, that's the condition number basically. Like if I raise it to the nth power, that's going to get like the condition number raised to the n. So it gets a lot worse. So if you have like any sort of like poor scaling in the problem, like this is as benign as it gets and it's still kind of bad. If you have like a poorly scaled problem where you end up with like A to the n kind of stuff happening and it results in really bad, like sort of blowing up gradients and things like this.
One question, when we say we are taking a larger horizon, does it mean we discretize more or does it mean we increase the time?
Either way, like numerically, those are the same. It's just how many time steps you're backpropping through. Yeah.
So you have some restriction on what you should guess.
Nope, we can do anything we want. We'll try some of this. Let me, because this is so bad, I don't want to like do too much more of this because it's probably going to break pretty quickly. We can try all these things in the better version that we'll do next. Okay, so let's get back to this. Keep going. And like, okay, so that's the shooting thing. Basically, I do that mostly for historical reasons and like to show you how kind of bad it is. And we will basically not do that ever again. And I'll show you the better stuff now. So the beginnings of the discussion on like better things to do is this kind of LQR as a QP thing. Okay, so what I'm going to do now is like walk through that problem setup. That problem is kind of already somewhat obviously a QP as a quadratic cost and linear constraints, which we talked about QPs, right, when we did the optimization overview. So this is a QP. What I'm going to do now is just kind of massage it into the sort of standard form of a QP and show you what that looks like. So first thing is we're going to assume initial state is given. And so it's not a decision variable. And then we're going to just stack up all of the u's and x's for the whole trajectory into one big vector. And we're going to call that z. Here's what that looks like. So we're going to have, you know, u1, x2, u2, x3, blah, 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 dot, 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 all the way to xn, right? I'm just stacking up all the u's and x's over the whole trajectory into one big vector. And then, so that's kind of like your decision variables now. And then I'm also going to define a like big cost Hessian matrix that's sort of to go along with this z vector. So we'll call this H, and it's what you would expect. It's basically just me massaging. So I'm going to stack all the x's and u's into one big vector, and then I'm going to stack all of the q's and r's into one big block diagonal matrix that like corresponds to that z vector. So, you know, R1 to go with U1, Q2 to go with X2, you know, R2, Q3, dot, 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 up to Qn. So we define that such that the cost function now just looks like 1/2 z transpose h z. Does everyone see that? So like the whole cost function I have where it was a sum over time steps, blah, blah, blah. I'm just going to stack it all up in one big vector, stack all the q's and r's in one big matrix, and now it just looks like this, right? Nice little quadratic objective function. Cool. So I'm now going to do the same thing with the dynamics constraints. Let's write that on a new thing. So I'm going to define basically similar idea. I'm going to call it the matrix C and this right-hand side vector D. And it's just me writing the like xk plus 1 equals axk plus buk thing in like one big matrix. So this is going to look like the following. So I'm going to have B and then like minus identity, and then a bunch of zeros, and then A, B minus identity. These work. I don't have any good guesses, good jokes. So please work. Is it back? I think it's back. Huzzah. Okay, cool. We're back. Okay, so stack a bunch of stuff up, blah, blah, blah. And then, all the way to the end where it looks like, a n minus 1, b n minus 1 minus I. So this whole thing is sort of, multiplying u1, x2, u2, dot, 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 xn. And then the right-hand side is going to be, so remember, all this is just saying like ax, so like, the second row says, ax2 plus bu2 minus x3 equals 0, right? So it's just writing the dynamics constraints out in like this stacked matrix form. So the first line is just a little weird. And the only reason it's a little weird is because remember, x1 is not a decision variable. It's given to us. It's where we are right now. It's the initial state. So what I'm going to do is, I'm only optimizing over the b. So I need to get the ax1 thing. That needs to go on the right-hand side vector. So it's going to look like this. Minus ax1. So that now says, b times u1 minus x2 equals minus a times x1, right? So that lines up. That's giving us our dynamics. And then the rest of this guy is just zeros on the right-hand side. Okay, so these are our, this is our C matrix. This is our, awkward. Okay, so that's C. Then this guy is your Z decision variables, and then this guy is your D vector. And so now with that set up, we can write down like a standard form QP, like we talked about in the optimization sort of overview. Okay, so it's just min over Z of 1/2 Z transpose H Z subject to CX equals D, or CZ equals D. Everyone cool with this? Straightforward. Stack everything up. Yeah.
C matrix, should there also be a U to the bottom right?
What do you mean?
In the C matrix, we're going to get like A's fall down, B's fall down, I's fall down. Do we use this stay up there at the top? Or is there also zeros?
Oh yeah, sorry if that's These are zeros. There's zeros everywhere else. That's what the dots mean. Sorry if that was confusing. My handwriting is kind of terrible. Sorry. Okay, so this is cool. All right, so then what we're gonna do is like, we know how to do this now. This is just equality constraints. We know how to do that. We're gonna do the like classic Lagrange multiplier setup. Let's write that down. So we're gonna have L of Z and lambda. And so we just get the cost function plus Lagrange multiplier times our constraint, so CZ minus D. And then we can write down KKT conditions from this guy. We just set all the gradients equal to 0. So we get, say, grad of the Lagrangian with respect to Z is going to be HZ plus C transpose lambda. And this has to be 0. And then we get gradient with respect to lambda is just the dynamics constraint back again. So CZ minus D equals 0. I'm going to stack these things up and write them as a big matrix thing. And we get our sort of classic KKT system thing. Z lambda. And then right-hand side is 0 and D. Cool. Okay. So I basically did the, write the KKT conditions down, write down this linear system thing, KKT system. This is like what we learned about when we do Newton's method, right? So question, how many iterations of Newton's method do I need to solve this problem? One. It's a linear problem. So this matrix that I wrote down, which when we do nonlinear stuff, we get that matrix set up by linearizing nonlinear things. Here, it was linear to begin with. The KKT conditions are linear. So this matrix equation is exact. So I just solve one linear system and I get the solution. That's it. So there's no iterating, right? It's this is like kind of the magic of LQR. It's like got a closed form solution. It's one linear system solve, and that's the solution to LQR, right? That's worth kind of knowing about. That is neat. Okay, so now we're going to do this and compare it to the shooting thing that we just saw. It's kind of obvious. I can get the exact answer with one back solve, right? That's going to be way better than the weirdo gradient descent thing I did before. Let's sort of prove that out. Here's our code. Let's get rid of this thing. It's annoying. Okay, so same kind of stuff. We're going to set up the exact same problem. So there's our discrete time dynamics. This is the time horizon, 10 seconds, which is what I just did before. That took 2,000 something iterations, right? Initial conditions are the same, just starting at, 1 meter over. Same cost. Weights, identity 0.1 on the controls. Cost functions exactly the same. Now I'm going to build up my QP matrices. So this is that big H matrix where I just block diagonal concatenate these guys. I'm using some fun tricks. I like Kronecker products. If you haven't seen this before, it's lets you write these big block matrices down with a one-liner. It's fun. I don't know. I'm into these things. I use them a lot. So but this is kind of obvious what I'm doing, right? I'm just block diagonalizing this bunch of QR stuff, right? Cool. Here's that dynamics constraint thing. Here I'm just looping through. So I'm going to set this up as I'm just building that AB minus I pattern down. Again, using some Kronecker product tricks to expand that out and then doing some looping to put the A's in the right spots. That's the D vector on the right-hand side that we just talked about. So no surprises. Then this is it. I take that KKT system and I just solve it. It's H backslash, on that this guy, right? That's the linear system we just wrote down. And then I'm going to go through that solution vector Z and pull out the separate out and pull out the X's and U's from that big solution vector. So that's all that's going on. One backslash. So let's do it. I can plot everything. Look at the cost. Cool. So yeah, that looks exactly like what we just saw. And gets the right answer to way more decimal places than the shooting method. Awesome. Exact. Now we can go play with stuff, and this is going to work out a lot better because I can make this super big and it's going to be fine. So you guys want to try anything? Let's make R big and see what that does. So we expect that it's going to use less control and sort of take longer to get there, maybe. So let's do it again and see what happens. So this was, with 0.1, see what it does with 1. Kind of checks out. Maybe it's not that compelling. And make it like even bigger. We can make it 10. So yeah, now it's like taking way longer to get there. Anyone else want to try anything else? Thoughts? Yeah. Yeah, sure. Let's set this to 100. But yeah, so it's like just a bigger matrix equation, right? And it's no big deal. It's gonna like solve it basically instantly. So fine, there you go. Cool. Anyone else? Any other things we want to try? Yeah, what do you want to try? 75 for the state. You want to put a velocity on it? Minus 100. Why not? Let's try it. What's going to happen? No big deal. This is a very long horizon also. So like this horizon, the shooting thing would have barfed like for sure and would have not ever given us a good solution. So clearly this wins. Okay, cool. Any questions about this? QPs are nice. This is much better. Don't do shooting methods. Yeah.
So when we are increasing T to like 10 times more, like the matrix is also getting like 20 times bigger, right?
Yeah.
So how is inverting that taking like almost the same time?
Yeah, this is a fun thing. So you'll notice when I built these matrices, I made them sparse matrices. See, all this stuff is wrapped in sparse. That has a big thing to do with it. And this is what we're going to do next, actually. So yeah, it doesn't get a lot harder. So I made the matrix 10 times bigger, basically. And so like computationally, if you know anything about linear systems, it should be cubic. So it should be 1,000 times slower, right? But it's clearly not. It's still pretty cheap. So here's why. This is the next part. So anybody else before I get back to math? Cool. All right. So now we'll get into this like, complexity. Why is this fast? There's some deeper things going on. Okay. So what did we just do? So we did the double integrator again. Okay, so now what we're going to do is basically to get at that question, like we're going to dig a lot deeper into the QP. Specifically, we're going to take a much, much closer look at the KKT system. And some interesting things will happen. So okay, so first thing to note is that the KKT system for LQR is very sparse. And that's really the key to this. So that means it has lots of zeros. And it has a lot of structure. And when we say structure, whenever someone says problem structure, when they're talking about this kind of like optimization, they mean that the KKT system has like nice block patterns in the matrix. So it's got a lot of zeros, and then the stuff that's not zero falls into like some really nice sort of diagonally block pattern. That's what we call problem structure and optimization. So I'm going to write this down. I'm going to write down explicitly, like all the way out, the KKT system for LQR for like 3 or 4 time steps. I'll write it all out, and then we'll take a deeper dive into this thing. So let me write this down. So the cost, so the H matrix looks like this, and we're going to do the time invariant version. QR, QN. And let me like do some little ... So we're going to think about this as, the block. So that's the H block, and the C block underneath this looks like B minus I, A, B minus I, and then I should try to keep this to the little squares better. Cool. Okay, there's that. And then that's the little C matrix. And then C transpose up here looks like B transpose minus I, A transpose, B transpose minus I, A transpose, B transpose minus I. Cool. And then everything else is zeros that I didn't fill in. So there's a big zero block in here, and like everything else in the matrix that I didn't put anything in, zeros. The decision variable vector is going to be a bunch of X's and U's. Got a few time steps there, and then we're going to get lambda 2, lambda 3, lambda 4. Note I have like one fewer lambda, right? Because the constraints are like sort of in between the time steps, right? They're coupling the two time steps across. And then the right-hand side vector is a whole bunch of zeros over here. And then I've got that minus A, x1, and then zeros over here. Cool. So I wrote it out for a few time steps in like its full glory. And what we're going to do now is, has anyone done back substitution in their linear algebra class and seen like solving triangular matrices with back substitution? This is basically that. So here's what we're going to do. We're going to like stare at this thing for a second, and I'm going to look at the last line of like the up here. I'll circle it. So we're going to look at this line first. So I'm going to write this one out by itself. And it looks like this. So this says Qn x4 minus lambda 4 equals 0. So this is basically the terminal condition from the Pontryagin stuff, right? That's the last time step that kind of checks out. And I can take this and solve it for lambda 4. Cool. That's what we had from the last time step of Pontryagin. So no surprise there. Okay, cool. So I got lambda 4. What I'm going to do now is take lambda 4, substitute it back in, and go up to the next row. So let's look at the next row. Circle this guy. Okay, so this guy says, RU3 plus E transpose lambda 4 equals. Okay, so now I'm going to plug in lambda 4. So I'm going to get RU3 plus B transpose QN X4 equals 0. Cool. Now I'm going to plug in the dynamics for X4. So I can write it in terms of X3 and U3. That's the next move. So that looks like RU3 plus E transpose QN AX3 plus BU3 equals 0. Okay. And now I'm going to just take this guy and solve it for U3. Let's do that. Okay, this is interesting. I'm going to take this thing here, this big matrix thing in front of X3, and I'm going to call this matrix K3. All right, so now, it may not be obvious yet, but we've actually now like bootstrapped a recursion. So now I can like keep going up the matrix and keep playing this game all the way to K equals 1. I'll write this out for like the next step, and like hopefully this will become a little more obvious. Let me get another color. So now if I like go to the next row, this one say, maybe I'm gonna go to the next page. Okay, so now I'll like write this line out. This is gonna get boring, but like hopefully the pattern becomes clear. So that line gives me that. I'm gonna now plug in, I have lambda 4 already. I'm gonna plug that in. And get this, plug in the dynamics again. And get similar stuff. Now I can plug in this K3. So I have U3 equals K3 X3. So I'm gonna plug that in down here for the U to eliminate U and get it all in terms of X. And I get, now I can solve for lambda 3 equals Q plus A transpose QN A minus BK. And I'm going to be a little bit lazy with the indices times X3. Okay, this is it. I'm not going to torture you with this anymore. This matrix in front of the X here, that gives me lambda, we're going to call this P3. Just making stuff up. Now we're done. Now we have a recursion for K and P. I start at the end and I just keep going this, and I've bootstrapped a recursion that can keep going backwards. So I'll write the recursion out in the general case. So we got Pn equals Qn at the like last time step. That kicks us off, and I can get K sub K equals the following thing. And then I can plug that back in and get P sub K. And then I can just basically start at time n and do this backward pass thing, recursion for Ks and Ps all the way to K equals 1, to the beginning. This thing is called the Riccati equation or Riccati recursion. It is famous. But at the end of the day, it's literally just like me solving this sparse QP by taking advantage of the sparsity pattern. So I look at this thing, I realize, hey, it's mostly zeros. And if I'm clever, I can do back substitution up the blocks. I know I can recognize that bottom line at time n is easy to solve. So I solve the bottom line, take the solution, plug it back in, get to the next line, solve that line, plug it back in, go up, plug it back in, and I can just keep going and do the whole thing like this, right? Super nice. Yeah. Yep. This stuff. Cool. Okay, so that's clear. It's the same thing. I'm just solving the QP, but it turns out there's this really nice like back substitution trick I can play because of the sparsity pattern of this matrix. This will have deeper connections to other things in a bit. But like kind of the idea here is, you know, we can solve the whole QP now by doing a backward Riccati pass. So that gets us like the K's and P's, which like also are giving us the lambdas and the U's basically. And then we can do a forward rollout. To compute the X's and U's from the initial conditions. Okay, that's cool. There's a couple things to say about this. So one is a general QP, if it was dense, would have cubic complexity, right? So if I just treated this as like, you know, in this case, right, if I treat it as dense, I would have n, basically n cubed, you know, n plus m, like everything cubed, right? Cubic. So big N is the time horizon, and then little n is the state dimension, little m is the control dimension. It's cubic in everything, right? So this would be if those were the big dense matrix, everything cubic. This Riccati solution, though, which is kind of sweet. What do we think about this Riccati thing?
Linear, right?
It's linear in big N and the number of time steps, because clearly I've got this backward recursion that I just do n times. It's still cubic in the state and controls though, because ultimately I'm solving linear systems in here, like this guy, right? I'm inverting a matrix that's size of U in the K line, that R is the size of U, right? It's M by M. So that linear system solve is cubic. And then all these in the P calculations, all those matrices are size N. And so matrix multiplication is also cubic. So it's cubic in the state and controls, but it's linear in the big N now. And this answers your question about why it's not that much faster. So if you were naive about this and I made it 10x the horizon, it would be 1000x. But if it's only here, it's only 10x. Does that make sense? So now it's linear in the time horizon, yeah.
We not using the equations, the bottom half of the Riccati system.
We are, yeah. So those are the dynamic. When I said plug the dynamics back in, those are the dynamics, right? Does that make sense? So we're actually implicitly subbing those things back in. I just sort of like said the dynamics, but that's what they are.
Yeah, recognize this and do it automatically.
So yeah, when I made these sparse matrices in Julia, the built-in sparse matrix tools are not doing this exactly, but they're doing something smart. This is going to be actually a lot faster than the built-in sparse matrix stuff. This is like the best you can do, basically. The built-in sparse stuff is smart enough, though, to get close to this, which is why it still was pretty okay. Yeah. Yeah, okay, so if I just have a linear system and I do a back solve, like AX equals B, and A is n by n, it's n cubed. That's just like how expensive it is to do a linear system solve. So if I were to do the whole KKT system like that, it would be cubic in everything. Time horizon, state control, because that's how big my matrix is, right? Time horizon. Yeah, I mean, I can write it down. State dimension. And this is control dimension. That makes sense? And so the difference here is now it's n times little n plus little m cubed. Cool. And it should be mentioned that this complexity result also carries over to the nonlinear case for like trajectory optimization. Okay, so the even cooler thing, now we can solve this really cheaply and fast, and it's awesome, and we can do long horizons and get exact solutions to this thing. Even cooler though is, think about what we got here. I now have this u equals minus kx thing, right? When I do the back solve here, starting from time n, that has no notion of like whatever my initial state was in it at all, right? Not until I get back to the beginning. And what I've actually computed here is not just like a single solution for a given initial condition, which I got when I did the like, gradient descent stuff. Here I've actually computed a feedback policy. And I can take this thing and plug in any x1 and get the solution with a forward rollout for the states and controls. So this is even deeper. I have a feedback policy, not just a single solution now, which is extremely cool also. And there's some deeper stuff there to talk about also, but just pointing this out. We'll talk more about this. Instead of just a single open loop trajectory solution. Okay,
So
cool.
This problem though, LQR is often posed with infinite horizons. So is the sort of sketchy math way.
We're going to talk about that now.
Okay.
So now we're going to do it. Yeah.
So when you do this step where you have like inverse R plus B transpose.
Yeah.
And is there like guarantee that means it's invertible?
Yep. It comes back to the like R has to be positive definite thing. If R is positive definite and Q is semi-definite, then all these are guaranteed to be invertible. Those are why those conditions exist. Cool. Okay, let's do some stuff with the code. Yeah, what's up?
You say that get a feedback policy u equal to minus kx.
Yep.
How stable is that with respect to like errors? Because here we are assuming like a perfect, like we know the entire range of x and u, right?
No, we didn't actually have to know x and u at all to do that. Like x and u didn't show up anywhere in that Riccati thing, right?
Even if
The things that show up in that backward pass are A, B, Q, and R. That's it. There's no x's or u's in there whatsoever. So it works. And in this LQR problem, it's giving you a global feedback policy that works anywhere from any initial condition. I only have to do Riccati once, and then for any initial conditions you give me, I can just like plug it into the feedback policy and get the optimal solution, which is cool. Okay, so let's do some of this, and like there's some more things to point out here. So back to the exact same thing as before. Same dynamics, blah, blah, blah. Same time horizon stuff, same, for now, same initial conditions. Same cost function. This is being really slow for reasons that I do not understand. Cost functions, same stuff. Okay, here's the Riccati stuff we just wrote down. So yeah, maybe this will make it clear, right? This is it. So I start at time n, just depends on the cost function. Here's the whole Riccati pass. It just depends on the dynamics and the cost function. There's no states or controls in there whatsoever. And then this forward rollout is where I actually put a state in. So the forward rollout, I start at some initial condition x naught, and then I roll it out with the feedback policy and the dynamics, and I get the x's and u's. Oops. Does that make that clear? Okay, so let's do this and plot some stuff. And the point I want to make here is just that you get the exact same solution as the QP by doing this, which is cool. There you go. Now we can also do a couple other things. Oh yeah, and then like this guy works out same way. I can go and change the initial conditions now. I can change the x naught here, and I can do a rollout again. I don't have to do Riccati again. So I don't have to solve the QP again, basically. I can recycle that for any initial condition. Even cooler, going back to that feedback policy thing, I can roll this out with like random noise, right? And have a stabilizing feedback controller. So let's do that. So I'm going to add a bunch of random noise here along the trajectory. Let's see what happens now. And so you'll see like noisy stuff, but it's like stabilizing feedback and it's driving me to the origin, like with all the disturbances and noise and stuff. So I have this like stabilizing feedback policy that comes out of this thing, which is super cool. What else? Okay, that's that. Okay, and then this gets to this like infinite horizon thing. What I'm going to do now is plot the Ks. So this is a 2D state and a 1D control. So the K matrix is actually just two numbers, right? It's a like little row vector. So I'm going to plot the elements of K right now coming out of Riccati. What happens?
It sure looks like it's converging.
Yeah, so it turns out that in the infinite horizon case, which by the way is only a thing with the linear time invariant, the time invariant case is the only case where it makes sense. What happens pretty quickly is that things converge to steady state values in the infinite horizon case. So it turns out, right, there's this little transient thing. This is, by the way, this is the final time, right? So it so happens like basically if I have infinite time, what's happening here is, right, you're saying like to the solver, to the problem, like you only have a couple moves to do the best you can. So that kind of changes what you do. But if you have all the time in the world, then like it, you know, it doesn't really matter what time it is, right? That's kind of the idea intuitively. So this is cool. And it turns out in a lot of cases, in practically speaking, because of this phenomenon, we just take the infinite horizon limit for K and we just run a fixed K for, and we don't worry about like the time that, so when that backward pass, I get different Ks at every time step, right? But because of this, it converges to some steady state values pretty quick. I just take the steady state solution. It turns out there's easier ways to compute that like directly give you the steady state solution. In MATLAB and Julia, this is called DLQR for discrete time LQR. Plug in ABQR, it gives you that infinite horizon solution. So let's look here. What I'm going to do is compare that infinite horizon solution to our solution here. And I don't know why it's being so slow, but you'll see they match like to many decimal places. So we, converge to this infinite horizon solution pretty quickly. And so we can actually just roll out with that constant K instead of using the time varying K. And you'll see that like it's giving you pretty much the same solution. And that like it's not really actually giving you much win to like use the time, because like basically we've already basically converged to the origin before we're getting that tail behavior here, right? So practically speaking, most of the time, if you have a time invariant problem, you just run the infinite horizon version and that's fine. What else was I going to say here? And then the other thing that's maybe worth mentioning is like, I don't know what I want to say here. Yeah, so this is in discrete time. Basically, with LQR, there are a bunch of like nice, at least in the linear case, there are a bunch of nice stability guarantees. So basically, LQR is guaranteed to give you a stable closed loop system. So if I like plug this in, like closed loop dynamics are A minus BK. Right? If I have AX plus BU and I plug in U equals minus KX, I can change that into like, A minus BK times X. And I can look at the closed loop eigenvalues, and that's what you get. I'll get different ones if I like mess with the Q and R weights. So if I go and change this to be like, let's say I'm like, I want to be really aggressive and use a lot of control effort. So I make this like really small. See what that does. It's going to like slam me down probably really quickly. This is also going to change my my closed loop stuff. Where's that? No, I can run this again. Blah, blah, blah. I get like more aggressive gains and I can like try this. So yeah, you can see like I'm like pushing way harder on this thing. Cool. I don't know. Anything else you want me to try? Yeah.
Like a controllability assumption.
Yes. We didn't talk about this yet. We're going to talk about this maybe next time. So yeah, so we talked about the Q and R conditions, which come down to like this invertibility thing in those Riccati equations. There's another one, which is this controllability condition, which actually comes down to the Jacobians in the C. So I have like this KKT system. So the Q and R conditions basically mean that H, the Hessian, is positive semi-definite. The controllability condition comes down to the C matrix, those dynamics constraint matrices being full rank. So they're both just conditions that KKT matrix is invertible, it turns out. All right.
Just thinking in like sort of the, I guess the more normal way you do LQR in continuous time, it's a differential equation that's going forward in time, right? Like we can solve.
No. So you mean to solve for the Ks and Ps and stuff?
Yeah, again, infinite time horizon.
Yeah, so that it's an ODE, which is actually just so what we wrote out here is like, I did it this weird matrix sparsity way. It's also just the Pontryagin equations
In continuous
in,
time.
well, I did in discrete time, but the continuous ODEs you know about,
Yeah.
they're literally just the continuous time Pontryagin
Pontryagin
equations
applies.
applied to this LQR problem. And you get ODEs for P and K and stuff like that. And so you get the same boundary value problem though. You'll get a backwards, you get an ODE you have to solve in backward time, starting from Pn you get an equation that's like minus P dot equals, something with terminal conditions for Pn, and you got to integrate that backwards. And it turns out it's actually a gnarly ODE to integrate. So going back to our discussion of like ODEs, remember we talked about things being stiff?
Yeah.
Turns out the Riccati ODE in continuous time is very stiff. It's actually really hard to integrate in continuous time. So the discrete time stuff is generally just easier to deal with and better.
My question goes more to the point of like, common filtering just to do a problem with this.
Yeah.
Common usually start with the covariance yes at initial.
Yeah. So this is like a deep sort of thing with like the duality between state estimation and control. State estimation problem, time is reversed and you're going forward in time.
Okay.
And so there you start with initial conditions.
Yeah.
And like the Riccati stuff goes forward in time.
Right.
Whereas in the control version, you start with a terminal condition and you have to go backward in time.
Okay.
So there's the duality thing involves like time reversal as well.
Solving Riccati in real time for control makes no sense. But
You
it
kind of
does.
can't. Yeah.
Yeah,
I mean,
it
it actually does show up. So when you do MPC,
Yeah.
and you're basically solving this sort of thing online,
Right.
one of the ways to solve this thing online is to do a Riccati thing.
Sure, again, for finite time price.
Yep. You're never doing the infinite time thing online. I shouldn't say never. There are weird things where people do this, but they're kind of dumb. And
Sure, when it was with Coleman, though, you can do it.
in the Kalman filter, you end up doing this online for sure. In the control setting, you also do actually, depending on how you implement. If you do MPC,
Mhm.
again, the inner loop of everything is an LQR problem.
Right.
So a lot of the ways of doing MPC, the inner loop of the solver ends up solving this problem always. And therefore, one of the ways of solving it is by solving a Riccati equation. And this is actually quite common. And we'll talk about this more later. This is basically what iterative LQR or differential dynamic programming looks like, if you've heard of those things. They're solving a Riccati. If you use those to do MPC, you're solving this Riccati thing in real time online. So it is done. It shows up. Okay, that was a long digression. Anybody, any questions? I'll hang out for a bit. We're done for the day. This will all get posted. Play with the code. Highly encourage you to play around. Yeah.